I'm sure you've been told that physics is just basically all math. It is and it isn't. You know, up until now, we've been talking about graphs and sort of what might happen, physical significance of things. Today, I'm just going to go through talking about the equations that we use. Particularly, we're going to get to the kinematic equations. That's the title here. Now, the first equation you guys basically already know we can get from this position versus time graph. So if I look at this, I can use my y equals mx plus b slope-intercept form to know that on the y-axis I have graphed position, and on the x-axis I have graphed time. The y-intercept is given here as the initial position. It could be xi. I'm going to write it as x naught, just because that's the way it's going to appear on your AP exam sheet. The slope of a line, the slope of a position versus time graph, remember, is the rise over the run, or the change in y, the change in your rise, over the change in x, the change in your run, the time. Delta x over delta t, change in position over change in time. This is just the velocity. And so actually from this whole thing, we've really only gotten this idea that the change in position, position, or the displacement, x minus x naught, or delta x, is the velocity times the time. That's nothing new. That's basically what we got here. All right. So I'm going to highlight this because it's important. All right. Now, if we have a velocity versus time graph, we can do the same thing. And so I'll write my slope-intercept form again, y equals mx plus b. Graphed on the y is the velocity, equals, graphed on the x is time, plus b, my y-intercept v naught is my initial velocity. Okay, so what is the slope of a velocity versus time graph? Remember, it's the change in y over the change in x. What's graphed on our y? The velocity. So the change in velocity over the change in time. Now this change in velocity over the change in time, this is just the acceleration. Okay, so our slope of a velocity versus time graph is the acceleration. And so this equation doesn't get us anything different than this, basically, where we have v minus v naught is the acceleration times the time. Or you could write it as delta v is acceleration times time. Most oftentimes what you'll see, though, is velocity final is the initial velocity plus the acceleration times the time. So it's basically this, but the velocity is over here. This is going to be our kinematic equation number 1. All right, I'm going to put a 1 here. Now we can use this equation again to talk about the position. Remember from Mr. Anderson's video or one of the other videos that we talk about the change in position of a velocity versus time graph as being the area under the curve. And so if we found this area, that would be our displacement, or delta x. So delta x is the area. Now this area is made up of 2 parts. This area is made up of a rectangle, I'm just going to call R, and a triangle that I'm going to call T. So we'll take the area of the rectangle and we'll add that to the area of the triangle, and that will get us our change in position. So the rectangle area is pretty easy. If we just have time here, this is the base times the height, and so this is just v naught as our height times time. That gives us our area of the rectangle. Now to find the area of the triangle, remember it's 1/2 base times the height. I'm going to do the height first. So the height here, no, I'm going to do this first. So the base is time, right? Time. And then the height is actually, if this is like our final velocity, the height isn't just the final velocity, it's the final velocity minus the initial velocity, because it's just this little piece. So 1/2 base times the height, v minus v naught. Now, we're going to do just something a little bit funky here based on this equation right here. I'm just going to call this equation A right here. V minus V naught is acceleration times the time. And so I can substitute AT in right here. And so this term, 1/2 t, V minus V naught, becomes 1/2 time times acceleration times time. Or we could rewrite this term as 1/2 acceleration times squared. So this change in position becomes our initial velocity times the time plus 1/2 AT squared, where A is the acceleration. All right, now I'm going to put a box around this. This is going to be our equation 2, our second kinematic equation. The third kinematic equation, there's a lot of math involved to find it. Now, I'm happy to go through that or point you to a thing, but our third kinematic equation is going to be that the velocity, hard pass, that the velocity final squared is the velocity initial squared plus 2 times the acceleration times delta x, or most oftentimes written as just the velocity squared is V naught squared plus 2a. And this delta x, you can write it as delta x, or if you don't like delta x, it's x minus x naught, the displacement or the change in position. This is our third kinematic equation. These are the 3 equations that you'll use anytime that you have a position versus time problem or an acceleration problem. Now, the big takeaway with this is these 3 equations are only good for constant acceleration. If acceleration is changing, these don't hold true, because if the acceleration is changing, then you get a different shaped graph for your velocity versus time. You'll get a curved graph, and so that wouldn't work out. So constant acceleration. All right. I think that's it.